Welcome to our CathCAD software training series of videos. This video will provide training on material testing execution. This section will instruct the user on the test methodologies required to make measurements on catheter specimens to obtain the values of flexural, longitudinal, and torsional rigidities that may be compared directly to the CathCAD computed outputs. This training video's agenda covers the following topics. First, we provide background information on the CathCAD software engine. Second, we summarize the CathCAD modeling assumptions. Third, we define the concepts of flexural, longitudinal, and torsional rigidities. Fourth, we follow the processes for making executing measurements and decomposing the results into the three rigidities. And finally, we provide two measurement testing examples and provide critical feedback on their execution. The CathCAD software modeling engine finds its basis from two major sources. First, the software utilizes the principles found in classical lamination theory. In materials science, a composite laminate is an assembly of layers of fibrous composite materials which can be joined to provide required engineering properties, including in-plane stiffness, bending stiffness, and strength. A good reference for the viewer to read and review is the textbook Mechanics of Composite Materials by the author Jones. Second, the software utilizes the ovalization theory developed and published by Brazier in 1926. This model was first described in the published paper, The Flexure of Thin Cylindrical Shells and Other Thin Sections. This model is used to compute the kink radius buckling value and is also used in the ovalization model. The underlying modeling engine makes the following assumptions. First, the tube is long and thin-walled. Second, the materials used in the design are isotropic. That is, the material behaves the same in all directions when a force is applied. Third, the overall design exhibits linear elastic behavior, which also means the deflections imposed are small. Finally, the design as manufactured is perfect concentricity, and the lamination between layers is perfect with no voids. These assumptions also assume that the connecting layers never delaminate or separate from each other during the deformation process. The CathCAD software assumes the part or design being modeled in the software is after all manufacturing steps are completed, including any lamination or fuse-down processes. The inner diameter, outside diameter, and layer designs should be that of the actual part. The actual part should be representative of the dimensions as entered by the user into the CathCAD software. The CathCAD software assumes that the braid layer is completely encapsulated with the matrix material. If the actual part made has incomplete braid encapsulation with the matrix material, the CathCAD computed values will not match that of the actual part. Some CathCAD users have utilized the dimensions of the lamination outer tube before the lamination process. This methodology is incorrect and will result in incorrect CathCAD model outputs. A good way to check is to ensure the measured outside diameter matches the theoretical CathCAD computed outside diameter. This page summarizes the standard defining the terms flexural, longitudinal, and torsional rigidity. Flexural rigidity is defined as the force couple required to bend a fixed, non-rigid structure in one unit of curvature, or it can be defined as the resistance offered by a structure while undergoing bending. Longitudinal rigidity is the extent to which an object resists deformation in response to an applied force along the longitudinal axis. Torsional rigidity is the amount of resistance a cross-section has against torsional deformation. ASTM D790 documents the standard test methods for flexural properties. These test methods utilize a three-point loading system applied to a simply supported beam. This standard references ASTM 618, practice for conditioning plastics prior to testing. This page summarizes the derivation or data mining of the flexural rigidity value from an actual catheter device using the three-point bending method. The actual test fixture is illustrated in the upper left-hand corner of the page. The system consists of a mechanical stage, a three-point bending fixture, and a force sensor. The most frequent issue observed is the measurement sensor range is improperly sized compared to actual measurements. Always perform a measurement error analysis. Item 1 provides the kinematic equation that transforms device deflection to force applied, device length, and the flexural rigidity term, EI. Item 2 illustrates experimental data taken on the catheter devices. It is highly recommended, required by ASTM 790, to make multiple measurements. In our example, 3 parts were tested, and the results are provided for the user to review. Item 3 illustrates the experiment data reduced to the flexural rigidity, EI. The span length was 43.2 mm, the force applied was 3N, and the deflection was 4 mm. The resulting computed flexural rigidity value is 1,249.712 nmm asterisk μe. ASTM 638 provides the test method for tensile properties of plastics. This document is used to derive the value of longitudinal rigidity, or EA, from a test sample. This standard references ASTM 618, Practice for Conditioning Plastics Prior to Testing. This standard also requires testing multiple devices in order to obtain the best, most accurate value of the longitudinal rigidity. This page provides the derivation from measured force divided by strain to longitudinal rigidity, EI. This formula will be used on the test case that is illustrated on page 10 of this training session. We will note here that for an isotropic material, the E value derived from this exercise will be very close, if not exactly equal, to the modulus of elasticity value obtained from the flexural rigidity measurement. The CathCAD software assumes that the material is isotropic, that is, the material properties are the same in any direction. The CathCAD software assumes that the flexural modulus and longitudinal modulus values are the same. In practice, if we find that these values are significantly different, we offer the following guidance. Judge the importance of the flexural versus longitudinal directions in the design. If one direction is more important, then use that value. If both directions are important, then we suggest averaging the results. Please contact us if you have any questions, as we can walk you through the process. We now offer a numerical example of data mining or extracting the longitudinal rigidity value from a catheter sample. In this design example, we use the computed stress value of 1,284 psi at an elongation strain value of 0.5% or 0.005 inch. The computed EA value from the experimental data is 47.4 pounds, which compares favorably with the CathCAD computed value of 54 pounds, or an error of 12.2%. Different values of longitudinal rigidity are obtained depending on the secant percentage value that is used. These values are tabulated for the user. Note that the CathCAD software assumes small elongations, which is the reason that the secant value of 0.5% was utilized. And as a result, it provides the best matching value to the experimental measurements. A large secant value may be used, depending on your application. However, you will need to apply a correction factor to the computed CathCAD values to compensate for the larger deflection. ASTM 5279 provides the standard test method for dynamic mechanical properties in torsion for plastics. It is used to determine the torsional rigidity, GJ, from a catheter specimen. This standard references ASTM 618, Practice for Conditioning Plastics Prior to Testing. We now provide a numerical example where the torsional rigidity from measurement data, utilizing ASTM 5279. The experimental setup is illustrated in the upper left-hand corner of the page. It shows the tube sample, torque sensor, and a method to apply an angular deflection. Item 1 provides the key kinematic equation that allows the user to convert from measurement torque, part length, and angular deflection to torsional rigidity, or GJ. Item 2 provides experimental data derived from our test sample. The measurement data was reduced to the state where the x-axis was part rotation, measured in radians. The output value, torque, was measured as a function of angular position. Item 3 reduces the measurement data from item 2 into the required torsional rigidity value, GJ. Roth Technologies has had a large number of requests where the customer requested assistance in data mining experimental data to derive the effective rigidities of catheter prototypes. We always advise customers to review the measurement data prior to analysis. The mindset of the data analysis should be one of, this data is flawed until proven otherwise. In material test example number 1, we can see that the measurement data shows a stepwise appearance at every measurement point. This appearance is not normal and could be assigned to two possible issues. There is a mechanical stage translation issue and/or the force sensor was too large, which shows up as discretization in the measured data. Datasets like this example should not be used as the underlying values may be flawed, which results in incorrect data ironing via the equations provided earlier. It is the responsibility of the measurement systems engineer to ensure that the force sensor and mechanical stage translation system are working properly and sized properly. We always recommend a measurement systems error analysis be completed prior to analysis. In most cases, this may be done one time that can be applied to all test cases. In material test example number 2, we provide an example where the measured torque value was 0.05 lbf inch versus the CathCAD predicted value of 0.05 lbf inch. The first issue with this design was that the braid layer was not fully encapsulated with the polyamide matrix material. This resulted in a gross reduction in the torque capacity of the device. Referring back to page 4 of this training video, the CathCAD software assumes that the braid layer is completely encapsulated with the matrix material. If the actual part made has incomplete braid encapsulation with the matrix material, the CathCAD computed values will not match that of the actual part. The more interesting part of this exercise is executing a measurement systems error on the measurement data. The sensor utilized is a MR5050 and the indicator is Model 5i. The sensor accuracy is +/0.35% of full scale, which is ±0.175 lbf inch. The indicator accuracy is +/0.1% of full scale, which is ±0.05 lbf inch. As a result, the tolerance of the measured value is ±0.225 lbf inch. As a result, we provide the conclusio TN that the torque sensor utilized in the test was too large. The measured value is meaningless. The required torque sensor, full range, needs to be on the order of 0.5 to 1 Oz-inch full-scale range in order to measure the prototype. This example also illustrates the co-concept where the part modeled should be the same as the part actually manufactured. The inner diameter, outside diameter, and layer designs should be that of the actual part. The actual part should be representative of the dimensions as entered by the user into the CathCAD software. This completes our CathCAD training video. For more information, please visit our website at www.cathcad.com.